In 1926, Einstein sat at his desk stirring a nice hot cup of loose-leaf tea. As he does so, he notices a peculiar motion brewing. From our daily experiences, we would expect that the stirring of tea would result in the tea leaves moving towards the edge of the cup. This is obviously not the case here, as we observe that the tea leaves in fact move towards the center of the mug. This is known as the tea leaf paradox, which was solved by Einstein in 1926. In this demo, we will explain the physics behind this paradox.
Let's first consider a liquid at rest. So a small parcel of fluid with volume V has two forces acting on it, gravity acting downward and the buoyant force acting upward. The buoyant force arises because the pressure at the bottom of the glass is greater than the pressure at the top, and this pressure pushes liquid upwards. Now we consider when the liquid is stirred, and as we just saw, sometime after we stop stirring, the tea leaves collect in the center at the bottom of the cup. But why does this happen?
Let's consider the forces acting on the system when the fluid is rotating. First, when we stir the tea, we are making the fluid move. Because all of the fluid is moving, it is generating a centripetal force which acts towards the center. Next, there is also a force acting outward from the axis of rotation, commonly referred to as the centrifugal force. This is simply due to the rotation of the liquid.
This force from the center applies more force along the rim than in the center, so there is a pressure gradient force. More specifically, the pressure near the edges is greater than the pressure at the center of the mug, so the pressure gradient force acts inward. Finally, there is also an inertial force due to friction between the cup edges and the liquid. This friction force per unit area is the viscosity of the tea times velocity divided by some distance traveled.
With these forces in mind, we can now compare the flow of the tea in the center of the mug and the flow in the region of the edges and bottom of the cup, which is called the boundary layer. In the center region, the flow is simply defined by the balance between the centrifugal and pressure gradient forces, and acts approximately like a solid body. This means that each point within the fluid remains at constant distance from the rotation axis, so the velocity of the flow at all points in the center region is more or less constant.
Near the region of the walls and bottom of the cup, the friction force is more significant. It causes the angular velocity of the liquid to be less near these boundary layers than in other places nearer the center. So this explains why the tea leaves collect in the middle. But that's not all, because in the video we also saw that they collect in a pile at the bottom, and this we can explain by looking at the secondary flow.
When the fluid rotates, it tends to scatter in different directions, but the walls stop it. As a result, near the edges, pressure is higher than pressure at the center. However, at the bottom, friction causes the lower layer of the fluid to be at rest, and within this layer, there is no difference between pressure at the center and on the periphery. As a result, increased pressure at these points pushes the fluid down, and at the bottom, it has nowhere to go but up, and so this secondary flow appears. The fluid is both rotating and mixing, and it is this secondary flow that causes the tea leaves to move into a pile at the bottom of the cup.
We can also vary the reference frame and consider the case when the fluid is at rest and the cup moves around it. While the table spins, the viscous effects of the cup are now accelerating the water instead of slowing it down. In this case, what's essentially happening is that the pressure gradient is reversed and the leaves are pushed to the outside.
At first, as the cup rotates on the table, only the bottom layers are involved in rotation, and the pressure is greater at the edges than in the middle, whereas at the top, there is less of a pressure difference. So as the water flows from regions of high to low pressure, it turns out that the direction of secondary flow in this case is opposite to what we saw when the cup was not moving. This is why the tea leaves disperse around the edges instead of assembling in the middle.
When the cup stops rotating, or when the fluid moves faster than the walls, then we get the effect we saw before where the tea leaves gather in the centre. What's cool is that this experiment can also help us understand some atmospheric phenomena that occur outside of the teacup.
First, we can take the angular swirl of our teacup to be analogous to the rate of rotation of the Earth, omega. Consider a large atmospheric pressure system with a radius around 1,000 kilometers. In the case of these large-scale events, we can often neglect the apparent centrifugal force acting outward from the Earth's rotation axis, because the Coriolis force, which we can define as F is equal to 2 omega sine theta, will dominate the centrifugal force.
Now, if we take a low-pressure atmospheric system, such as in this figure, we can see a similar effect as we saw in our teacup. In the region of the pressure system far from the ground, the pressure gradient force inward is balanced by the Coriolis force outward, and this region is said to be in a geostrophic balance.
However, for regions near the lower boundary layer of the pressure system, just like at the bottom of the teacup, the influence of friction becomes important. The friction slows down the primary circular motion, and thus the Coriolis force is lower and no longer sufficient for the fluid to flow at a constant rate as a solid body. The inward pressure gradient dominates, and thus the air spirals into the center of the pressure low, and this is known as a subgeostrophic flow.
In order to better observe this effect, we demonstrate the path of an air parcel spiraling inward with a drop of food coloring, and a rotating reference frame simulating that of the Earth. We can see that the path spirals inward over time, just as the tea leaves did to form a pal, which is pretty neat.